Have you ever looked at a simple cutting tool? You know, the kind used in a lathe or a milling machine? It might just look like a small, sharp piece of metal, but packed into that tiny tip is an incredible amount of science, all designed to do something that sounds almost impossible, to cut and shape materials that are stronger than steel itself. Let's pull back the curtain on how it's done.
So that really is the million-dollar question, isn't it? We're surrounded by these amazing, super tough materials, things like titanium alloys, hardened steels, you name it. How on earth do you machine something that's specifically designed to resist being cut? That's the puzzle we're going to piece together.
Well, the answer is you fight fire with fire. You use a tool that is engineered to wage a constant microscopic war. On every single rotation, that tiny cutting edge is in a battle for its life against incredible heat, friction, and wear. It's a war fought at a scale you can't even see, and winning it is the secret to all modern manufacturing. Now, in this war, the #1 enemy is wear. It is a relentless force, trying to destroy the tool from the moment it touches the workpiece. And it's an enemy with many, many different faces.
So, what do we actually mean by tool wear? Simply put, it's the tool gradually failing because of the extreme conditions it's under. Think about the massive heat and pressure right at that cutting tip. It's an insane amount of stress. This slow, grinding destruction is the central problem that every cutting tool engineer is trying to solve.
And wear isn't just one simple thing. You've got flank wear, which is kind of like the tool's side being slowly sanded down. Then there's crater wear, where the super hot metal chips literally carve a canyon into the face of the tool. And of course, there's chipping, a sudden catastrophic failure of the edge. Each one of these is a different problem that demands its own clever solution.
Okay, so how do you start fighting back against all these types of wear? Well, your first line of defense is geometry. That's right, the very shape of the tool is one of the most powerful weapons you have in this microscopic war. Take the rake angle, for instance. It's a perfect example of an engineering trade-off. Think of it like a kitchen knife. A really sharp, aggressive angle, that's a positive rake, cuts easily, but it's also more delicate. A stronger, blunter angle, a negative rake, can take a beating and is great for tough materials, but it needs more force and creates a lot more heat. There's no single best answer. It's all about finding that perfect balance for the job at hand.
But it's so much more than just one angle. You've got the clearance angle to stop the tool from rubbing. You've got tiny microgrooves designed to manage heat. You've got the radius of the edge, which is a delicate dance between strength and sharpness. Even chamfering the edge can completely change how it resists chipping. Literally, every single curve is meticulously engineered.
So a perfectly designed shape is critical, but even the best geometry can't survive those extreme cutting forces forever. That's where the second line of defense comes in, materials. We have to give the tool a kind of microscopic suit of armor to help it survive the battle.
And these coatings make a huge difference. Just look at what happens when you're milling a really tough titanium alloy. The tool with the CVD, or chemical vapor deposition aluminum oxide coating, has way better wear resistance than the one with the PVD TALN coating. Choosing the right armor is absolutely critical for performance. And the results can be just staggering. By combining a specific titanium carbonate coating with the right coolant, you can get a 75% increase in tool life. Think about that. In a high-volume factory, that kind of improvement is a total game-changer, saving massive amounts of time and money, all from a coating that's thinner than a human hair. And it's not just about what you add on top. Get this, we also use deep cryogenic treatment. We're talking about freezing the tool to incredibly low temperatures. This actually changes the tool's internal structure, making it harder and more wear-resistant. The result? A solid 15% boost in tool life. It's like high-tech blacksmithing on a molecular level. Okay, so we have these amazingly engineered tools with custom shapes and space-age coatings. But how do you make sure a tool made in Germany works perfectly in a machine in Japan? You need a universal language. And for single-point cutting tools, that language is called ISO 3685. Now, I know what you're thinking. An international standard sounds boring, but it's not. This standard is the bedrock of global manufacturing. It's the reason you can buy a cutting insert from any company, anywhere in the world, and know it will not only fit, but perform exactly as expected. It's what makes our modern supply chains even possible. So what does this universal language actually define? Well, everything that matters. The exact radius of the tool tip, the precise cutting angles, the size of the shank, all of it. It even sets a clear, objective limit for when a tool is officially worn out, like when flank wear hits about 0.3 millimeters. This takes all the guesswork out of it. So we have the tool's shape.
It's macroscopic armor and the global standard that makes it all work together. But there is one final, crucial piece to this puzzle, and it's a part that's often completely overlooked: the tool holder.
The tool holder is the unsung hero of precision machining. It provides the rock-solid rigidity you need to fight off vibration, and vibration is the absolute enemy of a good finish and long tool life. It also positions that cutting edge with incredible accuracy. And now, modern holders are getting smart, with built-in sensors to monitor wear in real time.
And the innovation here is just brilliant. For instance, there are now self-propelled rotary tool holders that slowly, and I mean slowly, rotate the cutting insert as it's working. It's such a simple idea. It spreads the wear evenly around the entire edge instead of concentrating it in one spot. The result? A massive 67% increase in tool life. Just beautiful engineering.
So, when you put it all together, it's pretty amazing. From the microscopic geometry of the cutting edge to the advanced coatings acting as armor, all the way up to the global standards that let us work together, every single detail is engineered for one and only one purpose: to win the war on wear.
And that leaves us with one big final question. As we continue to invent ever stronger, lighter, and more complex materials for our cars, planes, and electronics, what will the next generation of cutting tools have to look like? What new breakthroughs in geometry, materials, and design will we need to keep winning this microscopic war? The future of how we make things literally depends on it.